Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Welcome to the SEI Podcast Series. My name is Suzanne Miller, and I'm a principal investigator in the SEI Software Solutions Division. Today, I am joined by my friend and colleague, Rick Kazman, a visiting scientist in the SEI Software Solutions Division. We're here to discuss software architecture patterns in support of developing and deploying robust, complex systems. These patterns were recently explored in the fourth edition of Software Architecture and Practice, which Rick co-authored with other friends and colleagues of ours, Len Bass and Paul Clements. Welcome, Rick. It's good to talk with you.
Good to talk to you, Susie.
So let's start by having you tell our audience that may not have heard from you before a little bit about yourself, what brought you to the SEI, and the work that you do here. And in particular, you have this unique connection to academia that not all of our staff do. So explain a little bit about your, it's not even bi-coastal, it's, I don't know what to call your situation, but yeah, we'll just talk about it.
World's longest commute. So I have two positions. I'm a professor at the University of Hawaii and a longtime visiting scientist at the Software Engineering Institute, also in the Software Solutions Division. I've had various affiliations with the SEI dating back to the 90s. In, I guess, 1998, Len Bass, Paul Clements, and I published the first edition of Software Architecture and Practice. It's now in its fourth edition, as you mentioned, which is kind of crazy to think. That I guess that means I'm old. And it's been a really interesting avenue for us for doing research and really practically grounded research. So all along, we've done a lot of collaboration with SEI customers, with real-world projects to inform and enrich what it is that we write about, what it is that we profess. So, for example, the technical report on which today's talk is based, today's podcast is based, that came out this year, but it was in turn based on an earlier technical report that came out in about 2009 that was based on some work that I did with an architect at Boeing on availability. So, we have a long legacy of doing work that has, I would say, 2 feet, one in the world of academia, in the world of research, and another firmly grounded in the world of practice.
And that is one of the things that I know about you, is that passion for making sure that academic work has a grounding and that we understand how to apply it, and which is, very much in tune with our mission here at the SEI. And the architecture topic in general at the SEI is very long-lived. It was one of the early initiatives at the SEI, and it is notable that we're still learning new things about architecture, both in terms of where we can apply older thinking to newer situations, both software and hardware, and new thinking about, as we get microservices as a pattern, for example, what effect does that type of architectural pattern have on things like availability, robustness, deployability, security, and those that so focus on quality attributes, I think, is the unique aspect of the SEI's architecture work. But it keeps on; it's the gift that keeps on giving, because there's always things for us to think about in those areas. And so let's focus today on availability, robustness, and what have you been learning recently about those topics in terms of architecture patterns, and especially cautions for some of our viewers who are architects that may not be aware of some of the things you've learned about, hey, if you engage in this pattern, it's going to reduce availability, or this pattern in contrast may improve it. So please.
Yeah, I mean, a lot of people will fall into the trap of thinking, for example, Well, I'm deploying to the cloud, so I don't need to worry about availability. The cloud takes care of all that for me. And while it's true the cloud does an awful lot for you and makes life a lot easier than what architects had to deal with 20 years ago, there's still a ton of decisions that you as an architect need to make. And you know, old architects, curmudgeons, will talk about how there's nothing new, right? That it's all been done before. These problems have all been seen before. But the technologies do change, and how we think about them does change. So we documented a bunch of patterns. Well, we documented, let's back up a second. We documented a set of mechanisms, what we call mechanisms, in the technical report. And mechanisms is our umbrella term for tactics and patterns. And tactics are the basic building blocks of architecture. And patterns, we like to say, are made up of tactics. So we say that by analogy, tactics are the atoms and patterns are the molecules.
Right.
And so the basic tactics really haven't changed much since 2009, since that TR in 2009. But in working on this this current report, which I should say was supported by and motivated by a government customer of ours, we realized that we did need to make that connection between the tactics, things like tactics would cover the basic ideas of how are you going to detect a fault? How are you going to recover from a fault? How are you going to prevent a fault? Those are the categories of tactics. And when you translate that into patterns, well, there's a lot of details. The details matter.
Right.
So that's a lot of what we focused on in this TR is listing those tactics and how to think about them, how to reason about them, how to analyze for them, but then really drilling down into the patterns.
And I'm guessing that some of this, you mentioned this at the beginning, the cloud is a different context of deployment than 2009. I mean, there were cloudish things in 2009, but the ubiquity of the cloud was not present at that time. So our architectural focus was not on, hey, make sure that all of our architectural patterns are robust to the cloud. Right. And so is that really one of the things that is driving some of the revisiting of these concepts?
Yeah. And even things like, so let me start off with a concrete example. Probably the most famous, most common availability pattern is triple modular redundancy. And that's where you have three identical components. This would be an instance of the active redundancy tactic. And they are processing the same inputs in parallel. And the idea is that if one of them goes down, well, you've still got two others. This also brings up the opportunity, and this is a part of the pattern that you often see for a voter. So if there's a chance that one of the components could fail live, that's to say it fails, but it's still spitting out something. Mm-hmm. You can look at the results and you say, well, two of them agree, one disagrees. We're going to mark that disagreeing one as bad and maybe do something to replace it or repair it. And we're going to still continue on with confidence, knowing that these other two agree and that, you know, we can continue processing without any interruption in service. So that's the most simple pattern. And that's the sort of thing that you can very easily do in the cloud. But something that's a little bit, let's say, more sophisticated than that would be the circuit breaker pattern. And the idea of a circuit breaker pattern is that there are often cases where a service fails and it takes a while to figure out that that service has failed. So some client sends a request to this service and then they wait and they wait and they wait and it times out. And then maybe they send another request and they wait and it times out. And this might happen several times before they finally decide, okay, I need to go to the backup service or do something else.
Right.
Report a failure. In the circuit breaker pattern, what you do is you have a monitor that is monitoring that service. And the monitor acts as an intermediary between the client and the service. And if the monitor determines that the service is no longer active, the client, which is now talking first to the intermediary, will immediately be told, sorry, no service today, right? And so it's a circuit breaker. You fail instantly, and that allows you to recover or reroute or do
Or
something.
Make a decision
to inform the user, whatever, do something much more quickly. So that's the sort of thing that a cloud doesn't just give you by default.
Right. You have to do something.
You have to do something. You have to think about what's the nature of the possible failures and what would I like to do? How would I like to respond?
Yeah. So I'm just thinking, I actually am seeing that pattern in my internet service. So now when power goes down in my house, I get a text message on my cell phone from my internet provider saying, hey, we've detected a power outage that may be affecting your internet service. And then when the power goes back on, they send me a message that says, we think the issue has been resolved in your area. So they're leaving it to me to make a decision, but they are giving me that circuit breaker. And honestly, it's gotten to where it's easier to see that than to call the electric company and say, hey, is there an outage in my area?
Interesting.
Yeah,
and you could take some recovery actions. Maybe you've got a backup power generator and you could go downstairs and fire it up, or you could just wait, or something else. Maybe you have a Tesla power wall and you fail over to that seamlessly. So and that's the idea. Is the pattern is patterns in general are technology agnostic.
Right.
How you instantiate them, how you realize them is going to make a big difference to things that you should and likely do care about, like mean time to failure, mean time to recovery,
or real-time processing that can't be interrupted. So many of our government customers, whether it's the IRS not wanting the service to go down when on April 15th, when everybody's hitting the servers to file their tax returns, or some of our military applications where there's a can't fail kind of mission. That's one of the things that's very important about robustness and availability, is that we have context throughout our world. I mean, my situation of, the internet went down. Well, that may interrupt us finishing this podcast, but nothing terrible is going to happen. But there are situations where bad things happen if service is interrupted. And so architects that are working in those areas really need to be aware of these kinds of patterns to make sure that they don't inadvertently cause a live failure or a system to go down when we can't afford it to go down. Are there new things that new patterns that we didn't really know about in 2009 that have either because of the cloud or just because of other parallel processing or other kinds of advances in technology that architects that have historically been working in these systems may not know about? Or there's some new things that we should talk about?
Again, there's nothing that's totally new. You could always find some precedent for one of these patterns, in a system that somebody built for telecom in 1978 or something like this. But there's certainly patterns that have come much more to the fore. In
more prevalent or need to be more prevalent.
Yeah, with the rise of the cloud. So one thing that's really popular is the health monitoring pattern. A health monitoring pattern, just if you think of the analogy of a health monitor, a patient monitor in a hospital that is beeping and is keeping track of a patient's heart rate and blood pressure and other vital signs. This is doing the same thing for a software component, some sort of process or some runtime component that you care about a service. And it may be a very simple thing, like the health monitor just pings the component periodically to see if it responds. Or it may be something much more sophisticated, looking at round-trip latency, looking at CPU utilization, memory utilization, or application-specific measures like percentage of this kind of requests that it responds to, or queue lengths, things like that. And this is becoming much more popular in distributed systems where you've got components that may be run by, operated by different service providers, maybe operating in different clouds, and you don't have a single way to assess the health of the system.
Gotcha.
And so you use these health monitors to figure out, is the problem over here? Is the problem over there? Should I send the physicians running? Do I need to do something? And this allows systems to be much more adaptive. And so, yeah, again, you could probably find examples of health monitoring in the past, but it's become very prevalent. There are entire companies whose existence is in observability frameworks, which are basically the foundation for health monitoring.
I would guess that health monitoring has also become more prevalent because of DevSecOps. Because I know some of the systems I've worked with, that is, how you are monitoring are things getting through? Do we have too many defects going through? Are there build problems? Is this build service giving us what we need, or is the latency too long in terms of how long it takes? And
are we under attack right now?
Or yeah.
Or can we distinguish very popular from under attack?
Yeah. So there's a lot of different contexts where health monitoring, and I hadn't really thought about the fact that with cloud, we do have distributed providers. And so if one provider is being attacked in some cloud environments, we have the option to switch. We just have to know.
Right.
And other times, maybe not so much, but that would certainly be one that we want to have people pay attention to.
Yeah, if your doctors didn't have all those diagnostics, they would be,
They'd have a harder time.
Yeah, very little use in actually making you better.
Yeah.
Another thing that's related to that, but a little bit different, but it again has become much more foundational, I would say, in cloud environments, in service-based systems, and microservice-based architectures, is the throttling pattern.
Is the which pattern?
Throttling.
Throttling. Oh, I thought you said throttling. Okay. Throttling pattern. Yes, I have heard of that one.
Yeah. So the idea there is that you might have, let's say, a service level agreement that you have pledged to maintain, but you can only maintain that if you're not dealing with more than X requests per second.
Right.
And so if requests per second go above that, you need to throttle those, right? There are other options. As an architect, I could try and increase resources. I could try and increase parallelism, increase the size of server pools and things like that. But at some point, you may not be able to increase resources infinitely, or you may have a bottleneck that you just can't get around. And so one option, not the only option, but one option for an architect is to throttle demand. And this could be rejecting certain requests. We're not going to deal with the low priority requests. We're only going to deal with the high priority requests. Or it could be, well, these requests have already gotten so much resources, so we're now going to serve the ones that have gotten less resources. So the throttling policy is up to you.
Mm-hmm.
But the core of the pattern is monitor demand in some form. And again, that could be queue lengths or average response time or something like that. And then when that exceeds some threshold, you start rejecting or delaying or deferring certain requests. And
this is another very popular pattern in telecoms. This is when we guarantee this much data at this speed. And if you go above that, then you're going to get throttled. They don't say it that way, but you're going to get throttled down to a lower speed until your next, month of service, your next period of service, or in case we have extra resource, we'll bump you back up.
Yeah, and you kind of see that in video conferencing systems where sometimes rather than losing a connection entirely, you'll go to a lower fidelity.
Right.
And the images start to get jerky and the voice starts to get choppy, but you can still, at least some of the time, make out what's being said. So,
or even where you decide to turn off your video because that reduces the bandwidth,
right.
right? And so you can get a better audio signal. We've all run into that from time to time.
Yeah.
Uh,
Yeah. So those are human instances or human controlled instances of throttling. And yeah, we've all done that, especially in the last couple of years.
Yeah, exactly. So we have the technical reports. We've got the fourth edition of Software Architecture Principles and Practices. We have courses based on that. So those are a few of the resources that we will mention in our transcript for this. But are there other ways for people that are not as familiar with, especially using these kinds of patterns in the cloud, that you would recommend for architects, either architect students or architects in practice, to go find out more about how these patterns affect robustness and things that they can do to increase the robustness of their particular applications?
Yeah, so there's a ton of resources these days on patterns available everywhere. Wikipedia and Stack Overflow and Reddit. You name your favorite technical community. And search on availability pattern or robustness pattern or something like that. You're going to find something.
Mm-hmm.
But I will say that we put a lot of thought and a lot of effort into this technical report. It's probably the longest technical report I've ever written. And so that's a pretty good place to start.
Okay.
It's a pretty comprehensive guide. We talk about what robustness is, and we talk about how to specify it in terms of robustness requirements.
Gotcha.
How to create scenarios, robustness
Mm-hmm.
scenarios. We talk about the mechanisms, the tactics, and the patterns. We provide a whole bunch of analysis techniques. So ranging from fairly informal questionnaires and checklist type approaches to much more formal Petri nets and Markov models and things like that, which of course we don't, there are entire books written on this topic, but we give an overview and then lots and lots of pointers to the relevant literature.
Sure.
And then at the end, what we provide is a playbook. And a playbook is something that we've done in the last few quality attribute reports. And the idea of a playbook is, well, just what it sounds like. It gives you a set of steps that you as an analyst can walk through to figure out, have I thought deeply enough about robustness? Have I asked the right questions? Have I collected enough information to be able to do analysis? Can I figure out if the requirement that I have is likely to be satisfied by the architectural decisions that have been made so far? So that's the very end of the report. And I think that if you haven't had a lot of experience in designing for and analyzing for robustness, looking at that playbook is a nice way to structure your thinking, to organize your thoughts and your tasks.
Gotcha. So this is probably not something that is part of the robustness discussion, but it strikes me as we're talking about these kinds of patterns that for those that are in the cybersecurity community, right, availability is a security issue as well. And, and many times our quality attributes are synergistic. Sometimes they're contradictory, but this is a case where they tend to be synergistic. Are there any of the patterns that contribute to robustness that come to your mind immediately? And, oh, by the way, this is a really good pattern to be aware of if you're trying to build in security, which we hope everyone is trying to do.
Well, for sure, as you and I already said, all of these monitoring patterns are really useful for monitoring liveness, availability, but you could monitor other stuff as well. So you can monitor patterns of attacks, for example, or patterns of connection requests to determine whether those are likely attacks. Another pattern that we didn't talk about is forward error recovery.
Mm-hmm.
And this comes from the telecom domain. And that's the idea that you add on to the payload that you're delivering some additional information that you can use to check the validity of that information when it arrives, right? And this is kind of one of the key ideas behind blockchain-based architectures.
Mm-hmm.
So that's another pattern that we talk about in the technical report that I think you could argue that has applicability to security as well.
Yeah. I'm just thinking about some of the people that I work with and multiple attributes like this.
Yeah.
Tend to, if you can get patterns that support multiple quality attributes, that's a real big win, especially if they don't have to be contradictory.
Yeah. Another one is there's a pattern called recovery blocks, which is basically a kind of end version programming pattern where you have different versions
Oh, okay.
of the same functionality.
Okay.
And that's something that's not often done, I think, for security. But it kind of makes sense that an attack that is successful on one implementation may not be successful on another implementation. So, I mean, I haven't thought deeply about this, but now that you bring it up, I think that
Your next technical note.
that might be a reasonable security approach. I mean, it's expensive to do end version anything.
Sure. Yeah.
But if you're really worried about security, and if this is really the nut of your system, the heart and soul of your system, you might want to think about protecting it in a, let's say, less traditional way.
So speaking of your next technical note, what is interesting to Rick Kazman right now, and what kinds of things are you thinking about, writing about, getting ready to teach more courses on for those of us that want an excuse to go to Hawaii?
Yeah, so there's two things. So I just attended the International Conference on Software Engineering, and it seemed like 4 out of 5 papers had machine learning in the title or in the abstract. And, in part it's low-hanging fruit. In part it's that our field, no different than any other field, is kind of fashion-driven or trend-driven.
Mm-hmm.
But, for sure, this is another tool that's now in the architect's toolbox. And so we're thinking a lot about what does it mean to create machine learning enabled systems? How does that change the architecting process or the requirements gathering for architecture process? Do we need to think about architecting in different ways? So that's definitely a technical report in my future, at least.
So machine learning, I mean, one of the ways I think about it is the learning aspect is loops of learning, right? And that to me connects very strongly to architecting for evolvability. Because if I don't, how can I allow learning to occur if I haven't architected for evolvability? So that may be a connection to the machine learning that would be interesting to explore.
Yeah, it brings up all kinds of challenges, like how do we monitor our models to ensure that they're still appropriate, they're still
relevant,
they haven't drifted too far away. How do we think about modularity and modifiability for machine learning models?
Yeah.
Right. Not something that data scientists really were trained to do, but as these things are becoming components in big systems, you start to have to think about that.
Right.
You can't treat everything as a brand new monolith. That's what computer science as a whole has evolved away from over the last decades.
Okay, so you're not ready. You may be old, but you're not ready to retire yet.
Yeah, maybe I got a couple more at bats left in me.
Yeah. No, I have always appreciated your thoughtfulness, Rick, and I know you're always thinking about how do things connect to other things, and so it's always a joy to talk with you about these things. And you get my own, as I just proved, you get my own thinking going. It's like, well, what about this and what about that? So I hope that this is also of interest to our viewers. And I want to thank you for talking with us today. As I said before, we will include links in the transcript to resources that we've mentioned, and a reminder to our audience that our podcasts are available virtually everywhere: SoundCloud, Stitcher, Apple Podcasts, Google Podcasts, and my favorite, the SEI's YouTube channel. If you like what you see in here today, we love it if you give us a thumbs up, especially on our channel. And my dad loves seeing my dad's 92 and he loves seeing how many thumbs up we have on our YouTube channel. So I want to thank you for joining us, Rick, and I want to thank all of our viewers for joining us today, and have a good rest of your day, wherever you are.
Thanks, Susie. Always a pleasure.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, Stitcher, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.